Hello and welcome to the 59th lecture in this series. Let's continue our discussion of differential forms in local coordinates. So we are talking about, actually we are just talking about open sets in Rn, and we saw that here we have a simple way of checking smoothness of a differential K form defined on an open set in Rn. The main observation is that we have a natural basis for the space of alternating K tensors, and in terms of the basis, smoothness amounts to saying that the coefficient functions are smooth, and we have proved one part of this statement. Now let's prove the other part. Now assume that Ci belongs to C infinity u for all strictly increasing multi-indices I. So I would like to say that then this is smooth. So now I have to start with arbitrary vector fields on U. Look at this function P going to omega P, x1P, xkP. Now what we can do is we can write each of the xi's as in terms of the standard basis. We have x1 equals a11 del by del x del x1 plus a1n del by del xn, etc. xk equals ak1 del by del x1 akn del by del x, where and we know that the smoothness of these xi's amounts to the smoothness of these functions aij. So these coefficient functions belong to, so I varying between 1 and k, j varying between 1 and n. So we have this smooth coefficient functions, and then just use multilinearity. So this function, let's call it, so this is, we have called it g of p. So then g of p is equal to omega p. Instead of x1, I just write a1 I del by del x I, etc. a k I del by del x I. Now strictly speaking, I should not use the same index I in the different sums. So, but just for notational simplicity, let's just keep it like this. Now the thing is that this, using multilinearity, what one gets is this will be summation over. So in fact now I'll be forced to use different indices. So here I'll have to say I1, Ik, Ik, where all this I1 runs from 1 to n, Ik also runs from 1 to n. Now, so using multilinearity, one gets A1, I1, AK, Ik, product of all these coefficient functions, and then omega p. Right, so here since I have taken p, so I have to put a p here as well. So this is P, this is P, so A1 of P and P, and here as well P. So I'll end up with this product and then omega P del by del x I1 at P del by del x Ik at P. Now, so these are, by assumption, these coefficient functions coming from the vector fields are smooth, so therefore the product here, this entire thing is smooth. So one just has to check that these things are smooth. So enough to check P going to omega P del by del x I1 at P del by del x Ik at P is smooth. Again, one is left with a similar thing. So here, just like in the previous step, previous calculation, you write omega P as Ci dxi again at P, and then this thing is also at P, so I won't write at P. Notation becomes a bit messy. So, but if I plug in these coordinate vector fields, del x del Ik at P, as in the previous step, I'll end up evaluating dxi on all these things. Maybe let me just say, just to not to keep track of the indices, so let me use J here as the summation multi-index. So this will be, and if we call I equals I1 Ik, then dxj evaluated on these vectors will be 0 unless I equals j. So there essentially only one term will survive, and that term will be Ci at P. So these are smooth. So this is just CIP, and by assumption we are given that Ci are all smooth. Therefore, this thing here, what we wanted to check is smooth. So this is just Ci, and one is done. So that takes care of open sets in Rn. And in the manifold setting, now let U phi be a chart on M. Again, so we have, just like we had a basis for the tangent space, we had a, given a chart, we get n linearly independent vector fields defined on U. Since dimension of the tangent space is also n, these n vector fields form a basis. We called this the coordinate vector fields, and we get, similarly we can do the same thing for forms. We have a basis for each TP MP in U, namely each TP M star, the dual space. So dx1 dxn, where just like for vector fields, when I write dx1, what I mean is, So this is U and this is phi. So this is mapping to something in Rn. Here I have dx1 on Rn, and what I'm doing is I'm just pulling these back to, so phi upper star of dx1, etc. So this notation, I'll put it in quotation marks. This means actually just the pullback of the corresponding dx1 back to the, and since phi is a diffeomorphism of from, so this is what we have been calling U1, from U to U1, the derivative, the pullback map. Oh, by the way, phi upper star here, I should clarify this notation. It's a slightly misleading notation, but this is standard. When one says phi upper star, what one means is d phi. So actually phi is just a map of open sets. The derivative is a map of vector spaces, and we are using the derivative to pull back. So it's actually d phi star of dx1. So here also I should put quotation marks. Phi upper star is nothing but d phi upper star of, but one normally doesn't write d phi upper star, one just writes phi star. Since phi is a diffeomorphism from U to U1, we know that the derivative is an isomorphism from TPU to T phi of P U1. Is an isomorphism. Hence, whenever we have an isomorphism of vector spaces, the pullback maps induce isomorphisms of corresponding between corresponding spaces of multilinear forms. So d phi upper star is an AKTP U1 to AKT phi of P. Oops, this goes in the opposite direction, sorry. AKT phi of P U1 to AKT P U is an isomorphism for all K. Actually, let me, is an isomorphism for all K. Right. So therefore, the point is that, yeah, in particular for one forms, if I start with a basis for the dual space in of the tangent space in Rn, and I pull it back via d phi, I get a basis, corresponding basis for each TPM star. And in fact, we can do this for, since this map is here is an isomorphism, we can also conclude more generally, we have a basis for AK TPU, namely phi upper star, where by phi upper star again I mean d phi upper star of dxi, which we write as so these things again I just write as just dxi. So we use, in short, we use the same notation even though we are on the manifold. We'll use the same notation as if we were, as long as we are inside the chart, we'll use the same notation as if we are on open subsets of Rn. So everywhere, however, if you will want to know what it literally means, there is this chart map involved, which is omitted when we, in this standard notation, this chart map is omitted and you just write dxi. So if we carry over this discussion, whatever we proved for open subsets of Rn, then we can see that we have the following proposition: omega in omega km is smooth if and only if. Of course, this notation is and this statement is kind of odd because when I write capital omega km, automatically I'm assuming that omega is smooth. So what I want to say is that any assignment from k to this thing, any assignment p to alpha p in LKTPM, or what we are talking about is AKTPM, is smooth if and only if something happens, and that something is exactly what we had for open subsets of Rn. If and only if in any chart u phi Ci are smooth, where omega is Ci dxi. Omega restricted to u is Ci dxi. So I won't prove this, and I mean the proof already, there's nothing much to prove. Essentially, we have proved the statement for open subsets of Rn, and what we have to observe is that when we have a diffeomorphism, the smooth forms will go to smooth forms. So you pull back, essentially, if you start with the smooth form on the manifold restricted to the open set, then you pull it back to U1 using phi inverse, which goes in the opposite direction. And then this expansion of omega in this form, so you will be applying phi inverse, d phi inverse star to everything here, and the way dxi was defined, when you apply phi inverse star, you will just actually you will get the real actual dxi on Rn, and then you will end up concluding Ci composed with phi inverse is smooth, and so on. and the other way also is similar, right? So this is a useful criterion to have. And then we also had these operations, tensor and wedge products. So if omega alpha belong to, let's say, let's just stick to wedge products. Right now I will have no occasion to talk about tensor products anymore. For us, tensor products wedge products. So if I start with two K forms, omega Km, then we define omega wedge alpha. This is a new, this is a, oh, actually I don't need them to be in the same omega in this thing, alpha and omega L of M. So this is K plus L of M by, so I have to say what its value at, what I get at a specific point. So I just define this to be omega at P wedge alpha at P. So omega at P will be a alternating K form on TPM, and alpha at P will be alternating, will be an alternating L form. So I can take the wedge product. It is easy to check that omega wedge alpha is smooth. Now this can be done either using the local, using a coordinate chart and expressing omega and alpha in terms of the charts, or one can directly go to the definition and use vector fields as well. Both ways will show that this is smooth. So right, so one has this. Now the other thing is that we have this the pullback operation. Let F be a smooth map between manifolds if omega belongs to omega Kn, we get F star omega and omega Km. And again, what one is doing is one is using the derivative to pull it back from here to here. Now at this point I have to be, there is one small subtlety, which is the smoothness of F star omega. This subtlety arises because of the following reason. Suppose I want to go by the definition of smoothness, then I'll have to plug in K vector fields on M. So each of these xi are vector fields on M. Well, this by definition, first of all, let's write down what this really means. It is df upper star omega acting on x1, xk, and by definition this is supposed to be omega df acting on x1, df acting on xk. Now here comes the problem that we know that omega is smooth. It's a smooth form on N. So if you plug in k vector fields, I should get something smooth, a smooth function on N. So actually, let's see, let's take a point P. G of P equal to f star P x1 P etc. xk at P. So this would be by definition d f of P, and I'd be pulling back the form at f of P x1 at P xk at P. And this is omega at f of P dfp x1 x1 at P. Well, let me just write it like this, at P. So as P changes on M, I would like to say that now I know that omega of, when the input to omega are smooth vector fields on N, I know I get something smooth on N. However, the problem is, as we have seen before, x1 and x2 all the way up to xk are vector fields on M, but when I do df of those vector fields, I may not get actual vector fields on N. This, after all, the extreme case of f being a constant map will show what can go wrong. So in short, the input here on this right hand side for omega are not actually vector fields on the target. So we can't directly use the definition of smoothness of omega, but we cannot use smoothness of omega since dfp x1 at P etc. dfp xk at P may not be vector fields on N. For each P, of course, I get a tangent vector and to some tangent space on N, but I may not get a vector field. So the problem is easily overcome by working with local coordinates. Local coordinates to see the smoothness of f star omega. So let's I'll stop here. In my next lecture, I'll talk a bit more about this. Thank you.